supported by Patreon. Dear friends, thank you for supporting us on this platform. Stars seem to us to be eternal and ever-present wanderers of the universe. But this is just an illusion. In reality, they go through a series of metamorphoses, and their lives have a beginning and an ending. Born in the bizarre chaos of gas and dust clouds, stars burn brightly for millions and billions of years, only to eventually perish in a dazzling flash. And today, we will follow this fantastic path, together with many amazing stars. Our journey will begin in the middle of the mysterious Orion Nebula, a cradle for thousands of young stars. Then we will follow their evolution using the example of an amazing binary pulsar. After that, we will embark on a long flight among the star systems surrounding the Sun, from newly formed stars to mature main sequence stars. After that, we will make our way to the burning giant living out the last moments of its life, the titanic CW Leonis. And then we will fly past a celestial body that has already undergone a transformation from a bright star into a dark and mysterious object, a black hole. Here we will see how extremely strong gravity distorts and tears apart the very fabric of the universe, giving rise to amazing natural phenomena. Let's get ready, and we begin. Kosmo. First outer space. There are stellar nurseries richly scattered across the galaxy, with some of them comparatively modest in size. Others stretch for tens and even hundreds of light years. These are vast nebulae made up of interstellar gas and dust being inexorably compressed by gravity forces. Most of these tremendous clouds are barely visible against the abyss of space, but some of them can be seen from the Earth with the naked eye. One of these structures is the Orion Nebula, located 1,344 light-years away from the Earth. It is the middle object in the so-called Sword of Orion, a clearly visible line produced by three relatively bright light sources. Due to its large size and comparative closeness to the Earth, the nebula has been attractive for scientists ever since the early days of astronomy. It is hardly surprising, therefore, that this great structure is one of the best-studied space objects. It was the Hubble Orbital Space Telescope that beamed back first images of the Orion Nebula back in 1993, where the rich diversity of its colors can be appreciated. Most of the material was of a reddish or bluish-purple hue, while unusual bright green lines of some peripheral areas were revealed by spectral analysis. This phenomenon perplexed scientists for a long time, as the observed radiation did not demonstrate any chemical element known at the time. There was even a hypothesis that was put forward about there being a hypothetical element nebulium, argued to be not present on our planet, but allegedly amply scattered across clouds and space. However, with the advancement of science, it turned out that the light was emitted by extremely rarefied and deionized oxygen. This discovery accounted not only for the bizarre illumination of many nebulae, including our Sun. There are currently not less than 3,000 stars discovered in the Orion Nebula to date, as well as giant clouds of interstellar gas and a great number of protostars. All this amazing diversity of space objects is concentrated in an area of around 23 light-years in diameter, all of them continuously and elaborately interacting with each other. The overall mass of the material concentrated here is around 10,000 solar masses. Looking at the Orion Nebula closer, we will notice several clearly defined areas. The most outstanding of them is trapezium, also known as Theta 1 Orionis. It's an open star cluster about 300,000 years of age, made up of 8 main components. Some of them are binary stars, others have no companions. The brightest and most noticeable of the trapezium stars are 4 stellar systems designated by letters of the Latin alphabet. Located close to each other, they lie within an area about 1.5 light-years in diameter. Each of these objects' mass is within 15 to 40 solar masses, which means that these stars are quite young and hot. Theta 1 Orionis C is the most massive, as well as the brightest star in both the trapezium cluster and actually the entire nebula. It is a white and blue main sequence star with a mass roughly 40 solar masses, whose radius is 8 times that of the Sun. The object's surface temperature is approximately 45,000 Kelvin, and its luminosity about 250,000 times higher than that of the Sun. The radiation of Theta 1 Orionis C illumines virtually all the nebula around it, but there is hardly any interstellar gas in its immediate vicinity. This is the case due to the fact it is typical for objects of this class to experience exceptionally powerful stellar wind that scatters rarefied material far off. Having traveled a few light-years away from trapezium, we will see another remarkable system, which is Theta 2 Orionis. It is made up of 3 gravitationally bound stars located close to the so-called Orion bar, an extensive feature of hot gas emitting bright light. It was impossible to study this area for a long time on account of dense clouds of dust, and thanks to the James Webb Telescope, more detailed images of this region have been beamed back to us. The first component of Theta 2 Orionis is just slightly less massive and not as luminous as the trapezium's biggest star. As for its surface temperature, it measures about 35,000 Kelvin. The second component of the system is 15 times as massive as the Sun and 12,000 times as bright. The third component is as heavy as 5 solar masses, and its temperature almost reaches 14,000 Kelvin. However, it wasn't just bright stars that caught the researchers' attention. James Webb's infrared cameras allowed it to detect previously unseen objects, hidden deep within the clouds of gas and dust. Thanks to the telescope, about 180 so-called proplids have been discovered at the heart of the Orion Nebula. These are dense, dark protoplanetary disks surrounding stars that are still in the process of formation. One of these is Orion 294-606, a young protostar about 1 million years old, surrounded by a gas and dust disk about 300 astronomical units in diameter. Thanks to its being edge-on to Earth, we can observe its structure and size. It is expected to hit the main sequence phase in a few million years, and it will be accompanied by a system of several exoplanets and possibly their satellites. The night sky of these future celestial bodies must be a truly fantastic sight. Just imagine a multicolored luminous veil with the glow of a multitude of close and bright stars far more numerous than those seen from the Earth coming through. And now and then tremendous swirls of glowing gas cover half the sky, turning the night into translucent twilight. If we fly a little further and examine the wider region, we see that the bulk of the nebula is filled with scattered gas. The central part of the cloud is filled with highly ionized hydrogen, which actively absorbs high-energy stellar radiation. The temperature of this gas can reach 10,000 Kelvin, but it falls sharply towards the edge of the region. Temperature and pressure contrasts, as well as the collision of stellar wind streams, set material in space in motion, creating tremendous currents and vortices. According to calculations, some of them can reach speeds of up to 50 kilometers per second, and their size can be greater than the solar system. Also, in some areas of the nebula, thin strands stretching for several light-years have been detected, consisting of relatively cool molecular hydrogen, with admixtures of methane, ethane and water. Further out, we will see that the central region of the Orion Nebula is enveloped in a vast cloud of cooler, denser gas. The cloud of bright stars and the luminescence of ionized hydrogen intricately intertwine here, creating a beautiful multicolored curtain of light. Hidden behind it are hundreds of space objects, invisible in the optical range. But the infrared cameras of today's telescopes allow us to see through the veil of interstellar matter. By combining data from different sources, astronomers have discovered about 700 protostars at different stages of evolution within this region. Their concentration is noticeably lower than in the central part of the nebula due to the lower degree of gravitational compression of the interstellar gas. The absolute majority of these objects are very young by space standards and are still in the process of formation. According to modern concepts of stellar evolution, new stars form during gradual gravitational compression of large clouds of interstellar gas. Typically, as a result of this process, giant nebulae split up into a number of closely grouped gravity centers, which soon turn into protostars. Such clusters are called stellar nurseries, or more scientifically, regions of star formation. At a certain point, the internal pressure of the compressed gas compensates for the gravitational forces, bringing the protostar to a state of temporary equilibrium. The remaining material swirls into a giant vortex disk, with some of it gradually absorbed by the future star, and the rest of it, by contrast, expelled far beyond the boundaries of the nascent system. The growing magnetic field of the young star also plays its part. As ionized particles accelerate through its field lines and then rapidly escape from the vicinity of the object, it has been calculated that such flows can reach speeds of up to several hundred kilometers per second. As they collide with the gas clouds surrounding them, they create large-scale vortices and hemispheres called Herbig-Haro objects. In the process, part of the kinetic energy dissipates into light and heat, giving these bizarre structures different colors. In addition, the ultra-fast motion affects the surrounding material, spreading shockwaves across it, which incidentally are also captured by telescopes. Since stellar nurseries contain many closely spaced protostars, each producing several gas emissions, it is not surprising that Herbig-Haro objects exhibit an amazing variety of shapes and colors. Clearly, being essentially the result of a major cosmic collision, they are highly unstable and variable. Herbig-Haro objects rapidly change color and shape, and typically disperse completely over several tens of thousands of years. During this time, they cover between 1 and 3 light-years on an escape trajectory from their parent stars. About 400 such objects have been discovered so far, with their total number within the Milky Way estimated to be about 150,000. Perhaps one of the varieties of this awe-inspiring natural phenomenon is the bullets, hundreds of astronomical units in diameter, also detected in the Orion Nebula. Moving at incredible speeds, they easily pierce thinner hydrogen clouds, creating far-flung shockwaves in them. According to spectral analysis, the frontal parts of these objects contain atoms of iron that glow in the infrared. The bullets are estimated to be about 1,000 years old, and their origin is still a mystery. They supposedly originated from some catastrophic event. Moving on, we will soon find that the Orion Nebula is part of a much larger cosmic structure called the Orion Cloud. It stretches for hundreds of light years, accounting for virtually the entire constellation of Orion in the Earth's night sky. This is where the well-known Horsehead Nebula is located, remarkable for its bizarre shape. It is a dense dust cloud, about 3.5 light-years in diameter, clearly visible against background of a contrasting scarlet glow. Also close to the Orion Nebula, there is an impressive cosmic structure called the Barnard's Loop. This emission nebula, about 300 light-years in size, came into being about 3 million years ago, after a series of consecutive explosions of mutually close supernovae. After the shock-compressed gas jets mixed together, they produced a gigantic curved nebula, and the glow of several young stars, gathered in an open cluster, made it reddish in hue. For all its beauty, the Orion Nebula is a fragile and unstable object by the universe's standards. Stellar winds and pressure of light from many young stars as well as gas emissions and turbulent vortices, constantly disperse its material in the surrounding space. The nebula has already lost about 60% of its original material, and in about 100,000 years it will be stripped of its remnants. In place of the shiny, multicolored cloud, there will remain an open star cluster similar to the Pleiades. For a time, the young stars forming it will move together, but eventually each will find its separate way through the vast expanse of the boundless galaxy around. According to today's concepts, the life of any star is determined almost exclusively by its mass, with the star's mass being less than 8 solar masses. Having completed several evolutionary stages, it eventually turns into a white dwarf. It is assumed that after billions of years, it will lose the rest of its energy and transform into a hypothetical object called a black dwarf. This path is destined for more than 99% of the universe's stars, including our Sun. If the mass of a star exceeds 8 solar masses, however, its evolution follows a different path, eventually resulting in a supernova explosion. The outer shells of the star are scattered in the surrounding space, forming a scattered gas nebula. At the center of the system, there remains a supercompact and extremely dense object, the former stellar core. Its fate also depends entirely on its mass. If it is too great, the core of the dead star will not be able to resist the inexorable gravity and will inevitably shrink into a black hole. However, there is another way. In the case where the mass of the stellar remnant is within the range of 1.4 to 2.2 solar masses, a neutron star is formed. Gravitational forces in its interior destroy atomic nuclei, forming a super-dense neutron matter with rather bizarre physical properties. For a number of reasons, neutron stars are extremely difficult to observe and study. Firstly, celestial bodies of this class are extremely rare. According to calculations, there is only one such object per 1,000 ordinary stars. Secondly, they are very compact and practically do not emit light in the optical range. Therefore, before the advent of X-ray telescopes, it was impossible to spot these objects. Not surprisingly, the first neutron star was discovered only in 1967, several decades after the theoretical justification of their existence. This is largely due to an unusual phenomenon associated with the law of momentum conservation. Thanks to this effect, most neutron stars have a very high rotational speed, and the interaction of their magnetic and electric fields generates powerful bursts of radiation, repeated with a very clear periodicity. Such objects are called pulsars, and they make up the majority of neutron stars discovered so far. Their pulses are effectively detected by X-ray telescopes even at distances of thousands of light years. In total, more than 3,200 neutron stars have been discovered so far, and about 90% of them are single objects. The rest are part of binary and multiple systems. Most often, the companion of these cosmic bodies is a red giant or a main sequence star, but in isolated cases, another neutron star. This happens when two similar stars synchronously approach the end of their life cycle, and the explosion of one of them triggers the collapse of the second. Because of the loss of energy during the transformation, the remnants of stellar nuclei closely converge, which causes their mutual velocity to grow to enormous values. And according to today's concepts, this is how the amazing system called PSR J0737-3039 was formed. It is located at a distance of about 4,500 light-years from Earth and is quite unique. being made up of even two pulsars located very close to each other. The first of them is 34% more massive than the Sun and has an incredible speed of its proper rotation. Every second, the object completes 44 revolutions around its axis. The second pulsar is a little smaller and slower. Its mass is 1.25 of that of the Sun, and the rotation period is 2.77 seconds. If we want to take a closer look at these objects, we will see that their size is extremely small by space standards. Either component of the system is no more than a couple of dozen kilometers in diameter. As for their mass, it is actually comparable to that of most known stars. Due to these factors, the density of the matter that the pulsars are made up of is extremely high, and in order to understand this question, we need to look into their interior. The use of mathematical modeling techniques, combined with the theory of neutron star structure, allows us to learn even things not immediately visible. The outermost layer of objects of this class is the atmosphere. Incidentally, however, for neutron stars, this concept differs significantly from the familiar sphere of gas a planet is enveloped in, like that of Venus or the Earth. For both components of the system we're looking at now, this layer is no more than a few millimeters thick. This situation is typical for the absolute majority of neutron stars, but the youngest and hottest objects of this class may have an atmosphere of several dozen centimeters. It's made up of plasma, highly ionized remnants of stellar matter. Most of it is hydrogen and helium atoms, but heavier elements are also to be found. The next layer is the outer crust, which can be several hundred meters thick. The gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons, but it is enough to destroy the usual structure of matter. Elementary particles are all jumbled together, but still retain their internal integrity. Several powerful forces are pulling on the outer crust at once, such as gravity, magnetic field, electrostatic repulsion, and centrifugal inertia. This combination places the surface of neutron stars under constant mechanical stress. Occasionally, it builds up to a point where starquakes occur, titanic deformations of the surface of the cosmic object. As a result, there form mountains a few millimeters high and cracks up to a centimeter wide. These numbers do seem insignificant, but at extremely high gravity, a centimeter-high mountain is comparable to Olympus in the conditions of Mars. If we go still lower, we will see that this layer has no clear boundaries and goes several kilometers deep into the neutron star. As we dive into its interior, the pressure gradually increases, causing more and more electrons to be pushed into the atomic nuclei, initiating a reaction with protons. As a result, a neutron is formed, as well as a highly evasive particle called neutrino, which almost immediately leaves the interior of the celestial body, taking excess energy with it. In turn, beneath the inner crust, there lies the outer core, which consists entirely of neutron matter. This amazing substance is a multitude of tightly compressed neutrons, and its density is 10 to 15 times higher than that of the atomic nucleus. For example, our planet, compressed to the same degree, would have a radius of only 150 meters, and a cubic centimeter of its volume would contain several billion tons of neutron matter. In both components of the system we're looking at, the outer core continues as far as the center of the object. Incidentally, particularly large neutron stars should also have an inner core, according to today's concepts. Its structure is still a subject of scientific debate. According to one hypothesis, the pressure in the center of massive stars can be so great that it is capable of destroying even neutrons. forming a hypothetical quark matter. Such an object is called a quark star. Other assumptions allow for the formation of hyperonic or kaon nuclei, consisting of some bizarre matter with highly unusual properties. However, all these amazing structures are still within the domain of hypotheses, and to prove or disprove their existence is not yet possible. If we look at the system as a whole, we will discover several surprising and intriguing facts. First of all, we can notice that according to calculations, the pulsars in this system are moving rapidly around a common mass center along moderately elongated and very compact orbits. Observations show that the average distance between the components is only 800,000 kilometers, which is almost half the diameter of the Sun. Because of this small distance, the speed of mutual motion of both objects is very high. It exceeds 300 kilometers per second, so the pulsars make a complete revolution around a common mass center in just 2.45 hours. Such rapid motion causes a number of unusual phenomena due to the effects accounted for by the theory of relativity. For example, observations show that at the moment of maximum convergence of the pulsars, the period of proper rotation of each of them temporarily increases by 0.38 microseconds, after which it returns to the previous values. Even though this effect cannot be explained from the point of view of classical physics, the theory of relativity predicted it long before its practical detection. This anomaly is associated with the relativistic time dilation, which becomes the strongest exactly at the moment of maximum convergence of objects. Another phenomenon that stands out occurs during mutual eclipses and is associated with an anomalous redshift detected in the spectrum of one of the pulsars. The point is that the gravity of the component closer to us interferes with the signal from the distant object passing by it. Because of this, the radiation loses energy and its wavelength increases. It is also known that the orbits of these celestial bodies are affected by their interaction. This is reflected in the fact that the point of their maximum proximity, called the periastron, is constantly shifting. This phenomenon is called relativistic shift and has long been known to astronomers. It is usually recorded when studying fast celestial bodies. For example, Mercury's orbit shifts by 43 arcseconds every 100 years. As for the periastron of the binary pulsar, it shifts 140,000 times more strongly. Within a year, it deviates from its previous position by as much as 17 degrees. Thus, PSR J0737-3039 has the highest relativistic shift among all stellar systems known so far. If we leave the dry figures for a moment and think about hypothetical planets that may be hiding in this amazing system, their existence seems rather unlikely but still possible. Some objects, far from the center, did have a chance to survive the crushing double explosion of the supernovae, while others may have formed later. It is still harder to answer this question due to the fact that none of the widespread methods of searching for other planets are effective for exploring such systems. In any case, we cannot speak of the viability of the hypothetical celestial bodies of this system. The freezing cold and deadly radiation make them extremely inhospitable places. Observations show that this binary pulsar is constantly generating gravitational waves, causing the distance between its components to steadily decrease by 7 mm every day. This phenomenon occurs in all physical multiple star systems, but is usually too faint to be measured with any degree of certainty. This tells us that in about 85 million years, the pulsars will merge together to form a black hole. The tremendous cataclysm will be the source of super powerful gravitational waves that will travel through the entire Milky Way and reach other galaxies far beyond it. And the flash, accompanying the merger, may briefly become one of the brightest stars in the Earth's sky. In any case, the echoes of this devastating explosion will eventually fade without a trace in the infinity of the universe. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, On the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3,272 Kelvin, or about 3,000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths and a radius 20% greater than that of our planet. it is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multilayer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope Iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. A very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate, A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2 stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by 2 crimson stars circling the sky without stopping, while on the other side, the eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Although the stars we have visited are great distances apart, they are all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago. It is a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the solar system's motion is the so-called Bubble 1, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. "650 light-years away from the Earth, there lies IRC plus 10 to 16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin, or about 2,000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass is insufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, and amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is a comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen and stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around 1/1000th of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against the background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. It goes without saying that to detect a celestial object that absorbs all light shed on it is a challenging task, to say the least. That is why there are not that many confirmed black hole candidates today. Still, mathematical modeling shows that their number in our galaxy may reach 100 million. This may seem an incredibly big number, but since there are 200 to 400 billion stars in the Milky Way, it makes us realize that in all these expanses, black holes are objects one doesn't come across that much. In one of our previous videos on the topic, we mentioned that a star, the progenitor of a black hole, has to have a mass of at least 18 to 20 solar masses. Only this will ensure a powerful enough supernova to compress the scorching hot core of the star to an exceptionally dense clump of material. After this has occurred, nothing will be able to stand up to the object's gravity force and escape beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. What used to be a star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we're familiar with. The object referred to as A0620-00 or V616 is one of the black holes closest to our Earth that we know of. It lies 3,300 light-years away from our planet and forms part of a binary star in the constellation Monoceros. The other object in the system is an orange dwarf with a mass half that of the Sun. Every 7.75 hours, it completes a full orbit around an invisible object of unknown nature. Estimates show the mass of this invisible object to be around 6.6 times that of the Sun. It is admittedly too much for a neutron star. This leads one to believe that the bizarre invisible object is more likely than not a black hole. In addition to getting deformed and elongated by the more massive neighbor's gravity, the orange dwarf is also getting stripped of the outer layers of stellar matter. Spiraling streams of scorching gas gradually flow to the black hole and form a bright accretion disk. It is thanks to this dazzling disk that the black hole was detected. There are at least several dozen stars in the environs of V616, some of which almost certainly have their own planetary systems. It is highly likely that in the future, one of these stars will get dangerously close to the black hole and as a result will be sucked in by the object's insane gravity. This unfortunate star will have no choice, and in this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one. The process of interaction of a black hole with other objects largely depends on their mass ratio. The smaller the distance between them and the more massive the black hole, the stronger the influence of its tidal forces over its companion. The star may be deformed by them and get stretched towards the system's common mass center. They can also form channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object that is being sucked in by turning it into a fiery ring. It is assumed that there may be planets orbiting a black hole, just as if it were a regular star. In contrast to a widespread opinion, black holes are actually not able to suck in all objects around them indiscriminately. From the point of view of gravitation, In astronomical terms, they behave just like any star with the same mass. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several ways for them to form. Firstly, new celestial objects may originate in a nebula of gas and dust that is formed after a supernova. Influenced by gravitation, they first form clumps of material that collide with each other and attract cosmic dust. As a result, they eventually turn into planets and satellites, as well as large numbers of small celestial objects like asteroids and comets. The radiation of the black hole's accretion disk may be powerful enough to warm them and even melt ice on their surfaces. Hypothetically, a planetary system like that could be favorable enough for life to originate and, with any luck, evolve. Secondly, when a black hole captures and destroys another planetary system, some of its objects may choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all of its hydrogen and turn into a Chthonian planet. Thirdly, space wanderers like rogue planets or interstellar asteroids may also be ensnared by the massive object's gravity. Even though systems like that have not yet been discovered in practice, there is no reason to suppose they are non-existent. If, on the other hand, a planet is too close to the system's center, and the black hole is massive enough, other factors come into play. A scorching hot stream of material forming the accretion disk will strip the celestial object of its atmosphere, and its friction will slow it down and pull it still closer to the black hole. Eventually, extremely powerful tidal forces will rip the planet to tiny shreds. The debris will get pulled into the accretion disk and gradually melt in the hot gas around. In the end, they will inevitably get swallowed up by the black hole and, in essence, become part of it. It is posited that there are three main types of black holes to be found in the universe that are different first and foremost in terms of their mass. The first type can be found in the center of most spiral galaxies. These are gargantuan black holes with masses reaching several billion solar masses. The density of matter in the central part of a galaxy is generally extremely high, which is the reason why there originates a big number of large and bright stars quite closely packed. As they rapidly burn out, they transform into black holes, which in their turn rapidly grow and often merge with each other. As a result, supermassive objects are born, which are surrounded with giant accretion disks made of scorching hot material. They illumine space so brightly that it makes them seen from billions of light years away, even if their galaxy is completely unobservable to us. These objects are known as quasars. The second type is much more widespread, but at the same time, black holes like these are not that easily detectable. Their masses are close to those of stars, and they form out of large stars at the end of the latter's life cycle. By devouring other celestial bodies and interstellar gas, these objects gradually gain in size and eventually turn into intermediate mass black holes. They can also merge together, which generates gravity waves that distort space many light years around. The third type is the hypothetical primary black holes. Their existence has been inferred from today's theory of universe's origins and evolution. Fluctuations in matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate. It should be mentioned that according to estimates, the smaller an object of this type, the faster it evaporates, and at the end of its life cycle it turns into a tremendously powerful electromagnetic impulse. Modeling shows that primary black holes with masses around 10 to the power of 12 kilograms are supposed to be flaring up sometime around now, but to date, no such event has been registered yet. According to a certain hypothesis, a microscopic black hole may form on collision of extra-high-energy elementary particles. This variety is referred to as quantum black holes. Still, the conditions necessary for such an event to happen are impossible to be reproduced in lab conditions, and estimated life expectancy of these hypothetical objects is so small that it can hardly be measured with today's latest and most advanced methods. That is why quantum black holes still officially exist only in theory. Of course, it is extremely difficult to detect such dark and compact objects. Some of them happen to have a star companion, whose anomalous trajectory of movement gives telltale prompts of there being an invisible thing in close proximity. Another popular method of detection is observation of accretion disks. These object spectra have some typical features that allow telling them from other sources of light in space. Sometimes we're lucky enough to get a snapshot of a disk with a black spot in it that is evidence that the observed object's structure is quite unusual. A black hole may also be detected thanks to the gravitational microlensing effect. This involves detecting the massive invisible object as it transits between the Earth and a remote star. This changes the star's spectrum in a special way. But admittedly, this method requires a number of rare factors to successfully work. Incidentally, black holes are just one of the many possible endings in stellar evolution, possible only for the most massive stars. Every object in the universe is unique, and its path is unrepeatable. Studying stars allows us to better understand not only the boundless cosmos, but also ourselves. After all, we humans are only a tiny part of this vast, all-pervading mystery, the result of the long and complex evolution of stars and planets. And who knows what other amazing discoveries are waiting for us in the future.